Hello. Okay, so let's see what we have been doing. We started studying posets, order sets, and prosets. We reached like two interesting definitions of a lattice. One comes from an order theoretic perspective, which is like a special case of a poset, because it's just a poset that has some guarantees, and the guarantee is that it has all binary joins and all binary meets. And somebody else from a completely different perspective could have defined a lattice from an algebraic one. And then, depending on whether you like top and bottom or not, you could start with this definition. You have two binary operations. You list a bunch of axioms that you're interested in, and you have an algebraic theory because these are listed in equations and because you only have operations. But if you start from an algebraic lattice, you can define an order here. And as it turns out, I think nobody did this homework, and I don't know where I wrote it, but I'm pretty sure I wrote it somewhere. Like if I define an order, this set with the order that I have defined becomes a lattice in the order theoretic sense, and vice versa. If I start with this thing that happens to has all binary loops and GLBs, all binary joins and meets, and I define these operations, and now they are binary operations, to be, I don't know, that's the loop of AB, and similarly for the join, then these operations that I have defined here do satisfy all these properties. And in case I'm interested in bottom and top, same thing goes, okay? So they are really like two sides of the same coin. They're not different entities, but they have this like dual, this double aspect that you can treat them. And this is very nice when you want to prove things, because if you're working with with this relation, maybe it's very convenient to switch to an algebraic equational mindset and prove the thing you want, because after all, if you want to prove this, we know that this just means to prove this equality, and vice versa. This is the connecting lemma between like the algebraic point of view and the order theoretic point of view. Okay, so one of the theorems one of the homework that you were supposed to do, and none of you actually did, he's not here right now, and we discussed this a bit on Zulip, but this is an important discussion, and I want to bring it here also because I want to remind you that we are doing type theory, and we want to reach the idea of how proof assistants work. Was the uniqueness of, in a poset, the uniqueness of joins and meets. And as I mentioned in Zulip, when we say uniqueness here, we don't care about existence. Uniqueness, did I spell that right? Uniqueness of least upper bound, greatest lower bound. Uniqueness here always means at most one, including the possibility that there is none. So when I actually want to prove like there exists a unique thing, which reminds me that we haven't really discussed about this quantifier, it's a good opportunity to do that now. When I say there exists a unique, I don't know, U, because it's unique maybe, such that phi of U, so what this means is that you want to guarantee two things, which are at least one and at most one. We refer to this, the second part, this is what we refer to as the uniqueness part, and the other one is the existence part. Is uniqueness spelled like that? Yes, okay, thank you. So for this one, we already know how to express it in our language. It just exists U such that phi of U. Because whenever we say exists, it's implied that there exists at least one. And this one, I could write it something like that. There exists at most one U such that this, but I didn't really help anyone. Quite the contrary, maybe I confuse you because this will become sugar, and maybe you think that the principle, the kind of proposition that will become is existential one, but it's not. So this is like for all u v, in case both satisfy this thing I'm interested in, and there will be a spoiler for people who haven't read or watched Fight Club soon. So this is a warning. This is u equals v. So this is how we express at most one. In all of the universe I'm interested in, if you give me two things that have this property, I guarantee that they are equal. But notice that this is still valid if my universe is empty. Okay, so this is at most one, including the possibility 0. This is at least one, including an infinite witnesses of this fact. And how do we prove this? It's not a special kind of proof. We do what we know. So I say, suppose that I do have, this is always typed here, right? This of some alpha. Suppose then that uv of type alpha, such that, and I have that this satisfies these properties. And phi of v. So I suppose I have two things I'm interested in these things. They have the property I want, and my goal is to prove that u is equal to v. So the nickname of this proof, sometimes it's called proof by Fight Club. Proof by Fight Club. And notice this is not some kind of weird technique. I'm just attacking this, and then I'm attacking this, right? It's nothing special. Okay, so now that we have covered this, like what uniqueness really means, let's go to the uniqueness of least upper bound and greatest lower bound, and obviously this is only valid inside the poset, not in a proset. Pretty much this is the main difference inside the poset and proset. Poset guarantees certain uniquenesses, while proset would say I consider them equivalent, but I can actually see the difference, maybe. Okay, so I want to go to the proof of Raphael. I think it was Raphael who proved it, and I rewrote it in our language, so it will become very ugly. So that's on purpose. So let's see it. It's like that. So let's focus only on the GLB. So this is how I would write it here. What's the initial thing is that A is a GLB of x and y, and B, same thing, then A is equal to B. Okay, and what do I have in my context? I have a bunch of things, actually, because without this would never work. I have an A, a B, an X, and a Y. So I will sum this up. I have an A, a B, an X, and a Y, and all these live in some poset or proset P. So this is the theorem I'm trying to prove. So the first thing I want to do is suppose the left part of the implication, which is this one. So and I will give it a name, and I've called it hub. So far, what is hub then? It's this information that A and B are greatest lower bounds for X and Y. So it's a conjunction. And what I want to prove is this. So in the second line, I'm invoking the antisymmetry. I'm saying if I prove this conjunction, then I can get this, because this is exactly antisymmetry, right? Are we following? Okay. So I have two parts to prove. Luckily, the second part will be similar, so it's sufficient to prove the first part. So I want to prove that A is less than or equal to B. And now notice that hub is a conjunction, which means I can extract the left part and I obtain the left part, which is that A is a greatest lower bound of X and Y, and I give it a name called HA to remind me that is the main hypothesis I have here for A. And then I extract the right part from hub, which says that B is the greatest lower bound of x and y, and I also give it a name. But notice now that HA is a conjunction. It tells me that A is a lower bound of x and y, and it also tells me that A is a best lower bound. And similarly for HB. So each of these things itself is a conjunction, which means I can further extract information from it, and this is what I'm doing here. So I'm saying extract the left part of HA, and now I have this. And notice that I don't need to extract this right now. So I will not extract it. So I have here that A is a lower bound of x and y, and I'm calling this proposition hull. I hope you're following. It will be easier when we do that in Proof Assistant, but luckily we will not write in this annoyingly low-level way. Then I need to extract the other part of the information, the right part of the information about B. So in effect, I will use the fact that A is a lower bound, and I will use the fact that B is a best lower bound, and from this I will get a way to compare B with A. B is the best means it's greatest in this context, and it means that it's greater than or equal to any lower bound, but I do have that A is a lower bound, so I will obtain this. And I'm done with this part. And I hope you agree that this is an awful lot of lines of code, let's say, to write in order to prove something simple like that. But what I want to do now is emphasize this aspect of proof relevance and the fact that in my givens, I don't just have a fact, I have a witness for that fact. I have a proof of that fact, and this lies in the same table that I'm manipulating with the rest of the objects. So in the same way that if I have an f lying around, I can write f of a, and this is already meaningful. It's something of type vita, assuming that f is from alpha to vita. Or if I have a pair w, I can project left and right and get the two projections. So all these things are mathematical objects on my table, and I can manipulate them. And on the same way, I want to manipulate facts I know, because it's not just facts, it's witnesses of facts, proofs of facts, evidences of facts, programs of a type that corresponds to facts, if you like. So let's see what's going on here. Okay, let's rewrite this part in a better way. So let's see, what is the type of hub? So hub is this. I don't know if you can see. Can you see? Yeah, it's over there. Yes, Arati? Yes. Okay. Πρώτο τελευταίο apply here. I want to apply something to, okay, let me see what is HB. HB is this, right? Wait, this is HB, right? Sorry, you are absolutely right. Thank you. So we need to correct that on Zulip as well. I'm not applying, actually what happened, yes, thank you. So this, actually, no, wait, yeah, you're right. So this is not this, it's this, right? Is this what you're saying? Yes, I agree. So this is actually apply HBG. Thank you. So this is why you need a proof assistant. You say this would be a type error. Okay, so I think I skipped these two last parts when I was explaining this proof, and this is why this got unnoticed. So let's do that. From HB, I got the right part, which tells me that B is a greatest lower bound. And what does it mean? It means that for any C, if C is a lower bound, I get that. So I need to give it a specific C, and I give it A, in order to obtain this implication. And now that I have an implication, I need to feed it the left part in order to get the right part. This is the deal. Okay, back to my question. So what is the type of hub? What kind of thing is this? This hub that I have here, actually. Yes, Sarati? Okay, if we think about that, so this is the first time we are actually doing this. We think it's a proposition, but actually hub is like a proof of this proposition. And with a little bit of faith, we can say that let's identify propositions as types, and the idea is it's the type of all proofs of this proposition. So the type of hub is what corresponds to this conjunction. What's the conjunction? A is a GLB of x and y, and B is a GLB of an x and y. But conjunctions as a type correspond to pairs. That's the idea, and this is like one of the tables that we had there with comparing logic and types. And this is part of the BHK interpretation, which I will specify in a like couple of minutes. And since it's a pair, it means I can do things that I do with pairs. So it means that without having to think of a name, and remember, I value a lot this process of giving names, which means that if I can avoid it, I want to avoid it, because it's the most difficult part in a proof or a program, is to think of good names. So it means I can project. And now the question is, what are the type of those things? Somebody help me. Yes, Manolis?
The first is A GLB of x and y, and the second is B GLB of x and y.
Perfect. And this means that I can further project. Okay, let's remember what this means. What does this mean? Because it's like written a bit with sugar for humans, but what is written here? Yes?
A is lower bound of x and y, and every lower bound of x and y.
Good, so it's another conjunction. So it's A is a lower, not A is a lower bound of xy, and A is a best. Okay, and similarly for the next, so that means that hub point 1 is what? Because since this is a conjunction, it means I can further project. So this is, help me here, somebody else, okay, Panos, go ahead. Very nice, okay, so the point is, my big point is that I have never had to think of a name for that. I do have instant access in all those things. And this one starts becoming a bit definite because so far we only had conjunction implications. So let me project from the second of hub, let me project another time the second thing. So here I will have that B is best such thing. And if I remember now what this means, this means that, okay, I have a bug in my tablet. These pages are too short. Okay, so what does this mean? It means that for any C, something, and this something happens to be an implication, it's like if C is a lower bound, which I will write it, okay, let's skip this notation, then mine is better, is greater, so this is B. Okay, so now back to the BHK interpretation, it's like we were talking about conjunctions of only so far. Now here comes a for all, and for alls correspond to functions. So this means as a function I can apply to something. Of what type? I just have to look at this thing here, which was of type, a poset, right? Okay, so it's like some type P. Okay, and if I apply to this something of this type, then I get this thing substituting C for the input. So that means that like hub point 2, if I apply it, remember I'm just applying something, nothing special, to anything of type P. So I have some things of type P lying around. So I have to think now in which of these it will be useful to apply it. I have A, B, X, and Y. So what we did here actually was to apply this part to A. So let's go ahead and try to apply to A and see what happens. So what is the type of this thing? Remember, it was a function that was taking things of my universe to implications. So this will be an implication. So this will be like A is a lower bound of xy, then A is less than or B. So this means that this again is a function. Essentially then, this was like a carried function. It took this and that in order to produce this in order. So finally, this is my last line here, and I don't need any more, I think. Let's see. Hub 2, A. And now I need something of this type, an evidence, an inhabitant that guarantees that A has this property. And I do have one, and I don't need to break it further down to look at its components, because this is exactly the input that I want, something of this type. And where is it? It's this one, right? Can somebody help me? I want something of this type. It's this one. Yes, it's this one. Okay. So like one, what was it? One. And this has the type I wanted. And essentially, I can like delete all this. I will not do it because, let's say, for educational purposes I want it. But all this thing is useless, technically. I mean, my proof assistant does not need that. And this is already an object I have constructed that corresponds to a proof that A is less than or equal to B. And obviously, if I want to do the second thing, it's quite easy to figure out what it is. I could write similar, but let's say I'm actually talking to a proof assistant that does not understand this similar thing. And so probably I have to switch here some indices, and I probably have to switch like this A for B, and this will work out. So yeah, exercise for the reader, exactly which ones have to become 2 here. Or I could mix, you should not have like an obsession to proving something in a single line or something like that. You could say, okay, let's call HA and HB. These ones, let's call them so maybe now things become like more readable, because I want like the first property of HA. No, it was like, which property was it? No, from B, I want to say that it's the best one, and then I want to say what? I'm getting lost here. And again, this is why you need a proof assistant to help you with all those types. Okay, and there's another reason that I'm getting lost that I want to get to now. So okay, so far, any questions of what's happening so far? I'm trying to argue that the process of proving a theorem corresponds to the process of constructing an element of a certain type. The type corresponds to the proposition you are trying to prove, and the element you are constructing of this type corresponds to a particular proof. And this also gives a way to starting to consider what it means for 2 proofs to be equal, because we are comparing elements of a certain type. And we'll get to that part as well. But for the time being, I just want to equate these processes. I'm proving a theorem, I'm constructing an element of a type. And I construct this using like tactics. This is how these are called in proof assistant land, which look like imperative programming, orders, commands, do this, do that, obtain that, use this way. This reads like an imperative programming, or I can construct directly a type, and this will correspond to a more kind of declarative programming, like a functional programming, where you want to define a program of type that corresponds to this proof. Yes?
Can you reiterate please why the type of HAB is whatever you wrote?
Here? This one?
The justification that this is the type of HAB.
Okay, where was I? Because I started here. And this means I already had passed this thing on the left, and I said I will show you just this part. So I already had HAB was introduced in my scope from this line. So HB means is a proof of the fact that A and B are greatest lower bounds of X and Y. So this means it's a conjunction and stuff like that. You could say, okay, but how would I do that here?
Okay, so you see it as a proof, not as a proof.
Yeah, that's the whole point. Yes. So all these things are like, you can call them maybe proof objects, witnesses, programs, evidences, I don't know, of a certain proposition. Okay. So because I want to place them on the same table as the rest of the mathematical objects I'm manipulating, exactly because I want to do things like that. I want to apply an implication, after all, it's just a function, and I want to be able to apply it on an argument without saying something silly like R is equal to f of A. I don't need to be forced to give it a name. Like f of A is already something. Maybe I will do it for to help me with something. Giving good names is always helpful, but it's like I don't have this obligation. And I manipulate this object in the same terms as all the rest. Any other questions? Okay. So if you actually from what Sotiris asked, like what would happen if I said, okay, let's start from the previous line, which means that I don't have hub and somehow I need to introduce it as an object on my table, then I will look at my goal, which was an implication. So it means that since I need to prove an implication, I need to construct a function that takes me from things of this type to things of that type. And how I would do that? We know how to construct functions, just a lambda. And I could start like something like lambda x point and blah, blah, blah. But since the argument I will get here is this thing, A, G, L, B, X, Y, and B, G, L, B, X, Y, I don't want to give it a silly name like X because it will not help me. So I will give it the name hub, which helps me. So this is how this hub would have gotten introduced to my scope if I had chosen to start from the first line. And it's not like you will either do that when you're writing in a proof assistant, you don't need to make an a priori choice, I will use commands or I will build the terms myself. Proof assistants usually prefer one of the two, but you can choose the other as well. So you can do some things with commands, and then as soon as you see it, how to complete the thing, you can say, okay, it's just like this object. I see it now. Lean can work with both. It has nice commands that help you write things in a concise way. So the idea, the community, let's say, with Lean and Coq, it's more inclined to use tactics, but you can actually build the terms yourself, while Agda is inclined in the way of build the terms yourself, and I will help you build these terms. So in Agda, you are expected to build these things with a lot of help from the system. We'll see that in the second part, like after the Easter holidays. Any questions so far? Okay, so to sum up with this BHK interpretation, okay, you'll need to give me like 2 minutes because I need to figure out why my pages are smaller. Or I will cheat and do it like that. Yes, that's what I will do. Okay, I'll fix it later. So about the famous BHK interpretation, it's good to just call it BHK without worrying about the name. But anyway, this is Brouwer, Hating, and Kolmogorov, usually, although in the beginning it was a different K. So it's this idea of trying to say what the proof of something is and try to interpreting logic and proposition, not through truth tables, but through what it means to prove something. And just like the case of proof tables, where when you are doing this, and you want to, it's supposed to be a B, and you want to give it like the truth value of this, you are supposed to know the truth values of A and B. So you have like, I don't know, something like that, and you give like 4 values here, and this is a truth table. And in order to say them, to give the meaning, a truth table meaning of disjunction, let's say, you are supposed to know what A and B mean, and you consider all possibilities here and stuff like that. So in the same sense, when I will tell you what a proof of a conjunction is, you are supposed to know what a proof of the 2 parts of the conjunction mean, what it means to prove each of them. So I will give it always in terms of proofs of things that you are supposed to know how to prove. And we have pretty much done this. It's just that we haven't like placed it down as a systematic way. So like, what is a proof of a conjunction? It's just a pair of an A and B, where B is a proof. I will write this as is a proof of now. Is a proof of big A, and B, little b, is a proof of big B. This is what a proof of a conjunction is. It's a pair of things. So it means you can manipulate it. You can extract left and right and stuff like that. What is a proof of a disjunction? It can be 2 things. It can be either, the original interpretation here was like a pair again, but it can have 2 forms, either 0 and the proof of A, in case it was a 0, or it's N1, I will write like that, or it's N1 on the first thing, and then a proof of B. The whole idea here is that we're constructive, and I don't get to prove it in a weird way. I have to tell you which of the 2 I'm proving, and give a proof of this thing that I selected. The implication is just a function that takes you from proofs of A to proofs of B. So you give it a proof of A, and it gives you back a proof of B. Transforms proofs. It's like a program, a process that does that. So far, so good. What else do we have? A for all, which I write it like that, like this. If alpha phi of A. And this is again a function, but I will need now like this idea of dependent type. So it takes a little a of type A and gives back something that proves that A has this property. So why is it a dependent thing? Because my output here depends on which element I selected. If I select the natural number 2, let's say I want to prove that all numbers have a property. If I select the natural number 2 here I should have a proof that 2 is good. While if I receive the number 4, here I will need to prove that 4 is good. So the output is not always the same like it was in this case. It's a dependent function. It depends on what the input was. And if you remember this as a type, we write it like that. And the existential one is a pair, just like this junction. So you see a connection between these. I'm drawing a connection between these, and now I will draw a connection between these 2 as well. Is a pair where the first, here I have to select which of the 2 I'll prove, right? The first or the second. In this case, I will select which of the inhabitants will be my witness. So let's call it like W for witness. And then, which is of type alpha. And then I have to prove that my witness is indeed a valid witness. If I want to prove like that there is, I don't know, an even prime, I don't get to say, it's 8. It has to come together with a proof that 8 is an even prime. and of course it's not, so I will not be able to do that. But if I choose a different witness, I will do it. So this is also, what is the type of this thing? This is also dependent, because here I get like which we also write as that. So we have been pretty much absorbing some of these ideas like through osmosis a bit. So this is the time to give it a name. And this is exactly what happened here a lot in my process of explaining how this would work from this perspective. So we met conjunctions, implications. We had to attack an implication when I said this thing about lambda. We had to use an implication here. Notice it was even a carried one. What else we had? Like a for all and some conjunctions. I will not do another proof of this. I just wanted to like single out this concept, because I will need to refer to it. So, any questions? No. Okay. I do have like some 3 minutes left, and I think these 3 minutes are useless by themselves. But actually, no. I will tease you with something so that we can start the next hour. I'm losing my 3 minutes. Okay. So, let's say it's one of the things that will happen when we shift from our current mindset to include categories, is like we want to get rid of points. But when I say points, I mean the points we usually draw in diagrams and not any other points you might think. So like if you have a function from n, let's say, to n, this was a mistake, let's call it f, and let's say you define f to be like that. F of n is equal to, I don't know, n squared plus 1 and all this. Well, maybe it's good. I don't know, 2 times this. Let's say you have like this function. This function is given by using points. In what sense? I'm telling you where to map an arbitrary point n. So this guy here, I will refer to it as a point. And for this reason, this definition of f relies on points. It's a pointful, if you like, definition. And I would like to try to define it in the joke is that we call it pointless, but I will call it point-free. In a point-free way. And when you program like that, this has become increasingly popular. This is called tacit programming, when you avoid points. So I would like to write it like this. And notice that there is a way to cheat here and say, I can do it without saying f of n. I can always pass an argument on the other side and say, it's the lambda n, and then it's this. Okay? You didn't really do anything, right? I mean, you did not avoid points. You just passed the point on the other side. You kind of tried to hide it, but it's right here. I see it. It's right here. That's a point. This is the n. Okay, this is a little point. So let's not be silly. The idea is to try to prove this without seeing these points. I'm not talking about this point, obviously. Okay, so you got that. This is the point I'm trying to avoid. So, okay, let's have a break, and we will not discuss ideas of this during the break, okay? So it's a real break, and see you in 10 minutes, please, because we lost like 5 minutes in the beginning. Okay, so the idea is to try to get rid of points, and maybe it's kind of hard to justify why I would like to do that. But the whole concept is like we want to zoom out to have a clearer picture so that we don't mess with internal diagrams like these ones. This is one of the things to take away from a category theoretic point of view, we want like a bird's eye view. We want to zoom out so that we don't see these silly details, because maybe we are getting lost in the trees instead of the forest. We want to be able to express things in this level. And it's not just like a matter of preference. We see that we can generalize a lot and think more clearly if we do this on this level. Before we see how we can do that, there is something that we haven't like discussed, because we know we have the concept of clarification, but let's say you have to make a choice. Like, who here is team carried function, who is uncarried? Let's say you have to make a silly, let's say the person teaching this class is kind of silly and wants to make a choice. Okay, who here would be like team carried functions? Let's say carrified, right? Is that the word? It's not carried, right? It's, what's the correct term? It's I'm confusing English with Portuguese right now in my head, and I'm trying to think in Greek as well. So like this versus this. I don't. Do we call it carrified or carried? I think it's carried, right? Carried, whatever. I don't care about my accent right now. But like this, did I spell it correctly? It's like that? Yeah. Okay, and this would be uncarried, right? Okay, so I want to say like who here is like team, this team over here? 1, 2, 3. Okay, who here is team uncarried? 2, and Maya is undecisive. Let's pick a team. Okay, uncarried. Okay, so it's 3. Okay, usually the first time you see carried functions, maybe it takes you a while to appreciate it, and you think like, okay, I get the concept, but I'm used to this thing, I will stick to this thing. But if I ask you to justify that, I think that whoever voted for uncarried will have a kind of hard time to do that. Because it looks like if I have carried functions, okay, first of all, it's on a certain level, it's a silly question because we have defined two translations, carry and uncarry. So like, if your function is the one thing and you want the other, you can transform it, that's fine. And actually these are like subscripted with the arity, because you can imagine that, and for any n you have that, right? Like, if you have a function that has like a1 times an to some c, you can get the carrified, the carried, version like that, right? So we have a carry and uncarry function that translate for any arity, for any from 0, 1 to blah blah. So in a sense, you don't have to make a choice. But it's a valid question, like, when would you ever prefer to use this if this lets you do everything that the other lets you do, and even more, because you have a way to partially apply a function. So like, if you have plus as a carried function, let's call it plus, and you see it like that, I can define very easily a function like the successor. Let's say I did not have it. I could define the successor to be +1. Right? What is the type of +1? It got an argument. So it's this. And it's a function from the natural number to natural. Which function? The function that adds 1. So, I mean, the advantages of being able to, in a very easy way, to partially apply like a carried function is kind of obvious candidate for you to vote for this theme. Yes?
Yes, just to justify the cross product version, it's easier to graphically illustrate for small products what is happening and to visualize. Whereas the first one, if one never sees the cross product, it's almost impossible to visualize what is happening. For example, you have the notion of domain, and then you can think about...
you have a domain here, and a codomain here, right?
Yes, but the cross product tells you are in a plane, and then you can take subsets. It's really easy to see what you can do with it.
Okay. I think this has to do with you are more used to it. I don't think this is like an actual advantage of when you're about to use it, but maybe you have some point there. Essentially, you say you have to look when you look inside, you have some visual representation of A and B. It's some kind of plane, but although A could be person and B could be the integers, and that's not really a plane, but I get what you mean. Okay. So I think that, okay, Manolis?
I would actually like to say that.
To defend one of the two? No.
Actually, not defend really because I'm not sure exactly how to express my defense for the archaic version, but I want to kind of attack your argument for the archaic version. Because, okay, we can do that to get successful, for example, but if we wanted to plug in the second argument instead,
okay, so
we can use that.
yeah.
The archaic version,
Yeah.
we have projections.
Okay, so I mean, how would you do that? I like your attack. How would you do that normally? You have like some helper functions, right? Like you would have some function, let's call it flip, for example, that takes an alpha beta gamma to a beta alpha gamma, and whenever you want to do that, I would say that like, okay, for plus it doesn't make sense because it's commutative, but let's say it made, so you would do something like flip plus 1. But it makes sense. I get what you mean.
Then we have projections for the archaic.
And you can always use lambdas. I mean, you can use that even in this case. You can partially apply it like that. I mean, we like whole expressions. So actually, I could do it like this. If plus, let's call it add, actually, if it was like that, I could say that successor is equal to add like 1 and a whole, or a lambda x blah blah. It's just kind of more convenient when you don't need to do all this bureaucracy and you write something like that. And this is why actually it makes sense when you want to define a new carried function, what is the order of the arguments that I will use. If you always apply all of them, it doesn't really make sense, but usually you think of this idea. If I get which of these arguments only do I have a meaningful concept, and what's the second most meaningful argument to have, and the third one, and so you order them in the way that you think it will be more useful if you have something like that. Let's say. Okay, so, but what I'm about to show you now is like a very good argument, and I think it's the first, or I don't know if it's the only one, for appreciating functions like that. So let's go back to what we were trying to do here. Anybody has an idea how I could define that in a point-free way? Yes, Manolis. Sorry, Constantine, yeah, who has not spoken for a while.
Couldn't we define n as the nth succession, the succession of...
Wait, I want to define, I mean, a person defined this function, okay, and I want to define the same function in the sense that same input goes to same output, equality of function, extensionality of functions. So it's not like define a new function, you want to define like the same function f in a different way. So yeah, go ahead.
Yeah, my idea was, because we did all this conversation about carried and carried, to actually illustrate the point n.
We want to hide the point n. We want to do the opposite, right?
We want to hide the n, but to hide it in, in lambda calculus, like you can do the lambda, x, yeah.
Like this?
Yeah.
Because this is like the cheating way. You say you hid it, but you hid it only from the left hand side. It's right here, right?
Okay, if the nth number, the nth integer, in lambda calculus, I think that it's something like lambda of x. If we say, for example, 2 is lambda of x.
Yes, but let's not confuse this. What you're saying here is how to encode the natural numbers inside the lambda calculus.
Okay.
That's a different thing.
Okay.
We can let's consider natural numbers is an external concept, and indeed we can internalize it within lambda calculus. We are not doing this here.
No.
We do have the natural numbers, the normal ones, and so whatever I want to do, it has to do with this type, this set or whatever it is, and not some specific encoding of the natural numbers within the lambda.
Okay.
Okay.
The lambda calculus, it was only
An example.
Yes, I got my idea through the.
Okay, so okay, enough talking. Talk and say what do I write here, so that I will understand your idea. So let's say this person defined it like that. I would like to define it avoiding points.
2 times successor and successor in the power of n times.
How do you say n without n?
Yeah.
Okay. I think I get what you're trying to do, but you will have this difficulty, right? You don't have a name for your input.
Yes.
Because we are used, when we're defining functions like that, we are used to saying what you should do to the arbitrary input. And we're reading these things from the inside out. We say, take this n and do this, and then on the output that still refers to the n, do that, and then do this, and blah, blah, blah. We really need this n in this way of saying things. Yes?
No, I think it would be the same. I thought if we could define a unit in the set.
You mean like this?
Yes.
Well, you have access to this. The difficult point is to get an access to what?
Yes, it would be the same thing. So.
Okay. Manolis?
2 times the identity function squared plus 1.
Wait, I think you have a type error there. 2 times the identity function. Which identity function? The natural numbers, maybe?
Naturals.
Okay. And then what?
That's in the parenthesis. Identity function squared.
Squared, like that? No.
Yeah, the parenthesis goes before the identity. Identity plus 1.
Plus 1?
And then the parenthesis outside of that.
Like that?
No, the parenthesis, the right parenthesis of the identity.
Yeah, erase the.
Yes.
This one?
Yeah.
Okay, wait, we do have a type error here, unless you mean something very weird. Because since I'm adding 1 here, and I suppose this one is a natural number, then this must be addition of the natural number, so this should be a natural number.
Okay, sure, you can say that 1 is the constant function, but outputs 1 and then 2 is the same.
So this is a weird plus. It's not the plus of the natural numbers.
I mean, yeah, sure.
Okay. One more suggestion, Sotiris?
Yes, okay, it's just a random guess, right? That maybe instead of small n, we use the
Big N?
n.
And what?
As 1, we use
A small one?
type 1.
No, okay. Okay, let me give you the answer. You'll find it kind of obvious, but it's the idea of trying to describe not what f of n is, but what f accomplishes. So f in the end of times, it's just there, and you'll say, I could use that. You didn't say that. Yeah, I didn't say that, but you could use that. So this is the double of the successor of the square. And I'm done. So this is functional composition, which all of you know. I don't need to introduce it, I hope. And let's try to read that. First of all, if you are very used to seeing points, you will say, this is very weird, because I'm not used to that. But I want to argue that this is much closer to understanding what f really is. It's the double of something, and actually it's the double of the successor of the square. And if I write a complication expression there, probably you would also find a way to do that. And there is a good argument against what I'm saying, because in the same sense that I said this guy here was cheating, because I can still see the point, you could make the argument that I'm cheating here right now as well, because what is double, what is suck, and what is square? And first of all, it's not so cheating, even if you do something like that. I want also to argue, if you define it like that, let's use the same point, or maybe double. Let's say you defined it like that. And the successor, it's a primitive thing, so at least the successor, nobody will tell me something, because the successor is like the successor of the natural numbers, it's a constructor. This I do have. The other two maybe I don't have. And even if I define it like that, I have managed to give a definition of f which is kind of more, it's closer to what f really is. I've hidden, it's not a silly hiding, the thing of the point. I pushed it on a different level. Maybe these functions are more meaningful to you rather than a weird expression involving a formula with n and plus and whatever. But I could ask the way further, like, I'm obsessed, no, I don't want to see any points, so let's try to do this. I mean, how would you how would you define double? And many times when you program, or when you prove things, okay, you want to go from somewhere. Pretty much every programmer's objective when writing a program is like, you want to go from A to Z. A is your input, Z is your output. And you are required to write a program here, a function, that gets you from A to Z. It's very convenient if you can break it down into a simpler, cuter, better named things that may involve other intermediate domains. They could be equal, they could be different, I don't know. And your process pretty much ends up being the mental process, the creative process. Find good names for these, so that in the end, your program will just be the H of G of F. Or if you see it in diagrammatic notation, we will also use this notation for composition. Sorry. Do F, then cross G, and then cross H. It's the same thing. It's just the other way of writing the composition. So here, my objective was to go from n to n. Let's say I want to define double. Actually, in the beginning, I wanted to define this weird function. And I already managed to break it down into, okay, you know what? It's this, and you know you have a good modularity there, exactly when the functions you are defining are useful in their own right. I mean, I'm extracting here a very useful function called square, which probably I will use it again in my life, a successor, and here it's a double. All these seem nice and useful. And if you have maybe you can even have a good names for the intermediate ones, like this one and this, like this one. I don't want to do that now. So let's go here. And now my problem is to define this guy here, a double. Okay, how can I do that? I will repeat the process. I want to go from n to n, but now we'll think maybe I need to break it down in, I will let you guess what these functions are. I want in the end of things, in the end of times, to define this function as just the composition of two things that go from n first to pairs of n and then to n. So suggestions for this one. So I will start with a number, then I will get two numbers, and then the idea is that I will come back to a single number.
And plus.
This would be plus. Right? This is just the plus function. Which version of plus? Carried or uncarried? Uncarried. And voila, there is a nice argument of why uncarried functions tend to be useful, because they tend to compose things well. Whether if you have this carried function, your only hope here would be to call the carried function on it, uncarried function on it, so that it can be plugged together with the other things. And what do I have here? What's the idea? You start with an n. Let's cheat a bit. We will hide it so that they don't know that we dirtied our hands like with points. But let's say this should go to something, and then this should go to n plus n. So I already know what the pair here should be. N comma n, right? So I know what function, it's the one that sends n to two copies of n. And okay, maybe I never met this function before, but it's really probable that I have in my face an interesting and essential, useful function, something that duplicates its argument. We will call it a delta from the diagonal, and that's how it's called. And then I can also ask this, the same question. Okay, but what is delta? How would you define delta? And you can say, okay, enough with the silly things without points. I'm so low in a level that you will permit me to say that delta of n is equal to this pair. And I, of course, will say that you underestimate my silliness and my obsession. I don't want to see this point as well. Maybe I can do better. So the idea is to identify, if we can, certain functions that are like primitive, and from them I can define other functions just by composition. And this way, maybe you say, okay, delta looks like a primitive one, but we'll find out that we can do better than that. So this is just an idea of how you can work in a more distant way, defining functions in a less, in a way that has less clutter, and in a name that is way more meaningful and expresses better what the situation is. Any questions? Yes, Saradi.
Περίπου σαν αυτό που είπαμε τώρα, ότι προσπαθούμε να δούμε ποια είναι τα λιγότερα, αν μπορώ να...
Let's say that, yes, you want to avoid as much as possible defining things through points, because this way you may identify some concept in the level of arrows, and not like these arrows that don't have a bar, the arrows that go from domains to domains or types to types, and never mess with these kind of arrows that tell you that go inside the domain and look at the points. This should be mapped there. That's the idea. Before we finally start talking about a definition for categories, we might do it today. Yes, Panos. Two times, sorry. Yes, But in what sense? So you're saying that if you have some combinators, you can express the other functions? Exactly. But how does this answer the necessity or not necessity of...
So, every function...
An empty function, you said?
Every function...
Any function,
in lambda calculus and then transform to a combinatory form.
Okay, so you have it in a combinatory form?
Yes. So, even the function you gave here, so for example, that or something, you don't need to break it into a pair. You can represent it in lambda calculus and then transform it to the combinatory transform.
So you're saying that I'm curious, how would you define this in this sense? If it will have like a meaningful, like this function? Do you have like a...
Το έχω πρόγραμμα, γενικά υπάρχει ένας αλγόριθμος που δεν το θυμάστε, που παίρνει οποιαδήποτε συνάρτηση σε λάμδα λογισμού και μετατρέπει σε SKI.
Yes, but you get a combinator, but like this is not... I think this is kind of similar to what Konstantin said with the encodings. I mean, you can build any function there using these combinators, but did you really shed any, like, the idea is you have these things lying around, or maybe if you don't have them, you define them, and some of them will have outputs going to products or inputs going to products. So like you can combine them the way they are and not like have to translate them in I'm curious how this would work actually. I mean, if you can get a meaningful, I mean it's a debatable thing of whether it's meaningful or not.
So for example, you remember Miranda, the functional language?
Yes.
It was in the 80s. So what Turner was doing, he was taking a functional program, the form you have there, and he transformed it to SKI combinator from the way. So I'm sure it can be done. So the function you write.
Yes, you can write. Yes, I don't argue against this. You can write it, but like for me, it's like the thing of modularity. Like you already have these functions. Some of them output products or sums or whatever, some take this input, and you want a way to plug them together instead of, maybe if you want to work the way you're saying, you have to translate everything into SKI, and then maybe it will not be so human, maybe, I don't know. Depends on how fluent you are in the combinators, maybe. I'm curious to see that, though. It's an interesting point, to see how this would translate like that. Okay, so what was I about to say? Yeah, I don't know how familiar you are with what is called commutative diagrams, so I want to just use it to express the idea of something being like, let's say, a group homomorphism. And we know what a group homomorphism means. It means that it respects three things, because there are three protagonists in groups. So let me start with the easier one. And like to one surprise, there is one of arity 0, one of arity 1, and one of arity 2. And what are these? This is like the identity of the group, the inverse, and the operation. And surprisingly, the easier one is this one in the middle. So I will try to do this. So I want to express this idea that I have a group and another group, and something between them is something that respects the inverses, from group A to group B. So here is my group A, here is my group B, and I have a phi. If I draw it like that, with calligraphic A and calligraphic B, and I draw an arrow, it means that phi is an homomorphism. So what I want to say is that it respects the identity, and I want to say this by set of commutativity of a certain diagram. So I start from A, and I have two ways to go to B. The first one is like, I don't know, imagine there's a river here or something. You cross the river through phi, and you reach B. And now inside B, you can call the inverse of B, and you're still inside B, but you have the inverse of what you started with. And a friend of yours, instead of crossing the river first, went south by calling the inverse of A, and is still in the group A, and now decided to translate this result to B by calling phi. Okay? So what does it mean to respect the inverse? It means that the two ways are equal. So we write it like that. We put sometimes an equal sign like this. The idea, I'm comparing this path to this path. So if I say that this thing commutes, this means, I'm defining what commutativity of a square means. This means that this way, which is the inverse of phi, is equal to this way, which is the phi of the inverse. And be careful here, the inverses are different, right? I mean, this is the inverse B, and this is the inverse of A in the group A, and the phi is the same, okay? Why is it called commutativity? Because, I mean, I think it should be obvious from the picture of the square. If you go right and then, let's say, east and then south, it's the same of going south and then east. Okay, it's a commutativity. Does that make sense? Okay. How would you express that phi respects? So I can say that phi is an homomorphism if and only if it's a function from A and B, such that this diagram commutes, and I need two more things because it needs to respect the operation and the identity. The operation, as I said, I didn't say it yet, but this will be the most difficult one to visualize. It's a nice exercise, and I want you to think about it. So let's do this together, which is kind of simpler. Like you have you start from what? From 2 points in A, and you can operate on them, and now you are in A. By which operation? It's the operation of A. And now you translate this to B. Or you translate these things to B, each of them, so you are here, and then you operate on B. And the slight more difficulty that I have here compared to here is that here I already had a name for this, it's phi and phi, while here this is not technically phi. You may see this as phi, but it's like abuse of notation, because if I write phi here, I have a type error. What do I need here? I need a function that takes, say, a couple of a's and applies phi to each of them and gets a couple of b's. I don't know if you have seen this notation. We will end up writing this like this. And this has to do with this whole concept of getting functions for free. This is a general setting. I think I had a picture somewhere here. There you go. So, forget this first. As soon as you have like two functions, one from alpha to gamma and one from beta to delta, and alpha and gamma here and beta and delta are anything you like, sets, types, groups, whatever. As soon as you have these two arrows going like that, hopefully you can define a new thing that goes from pairs of alpha beta to pairs of gamma delta in the obvious way. Like you have a little a and a little b, and you can transform little a to some c of gamma and little b of some d of delta. It's the f of a and f of and g of b, and you can put them together. So you can always define this function, and we should have a criterion of when your definition is a good one, and this is exactly expressed by this commutativity. So you didn't pick some random thing that maps pairs of a's and b's to pairs of gammas and deltas. You said that it has to be consistent with my f and g in an essential way. What is this essential way? If I start, let's draw this. If I start here with an AB, and I project, I will get A, and then if I call F, I will get F of A. While if some other person does the other way around, first they call my function, this mysterious function that I need to define, and then they project, they should reach the same f of a, and similar for the other square. Okay? So I have a good criterion of deciding whether the thing that you're defining here deserves this name, or you're just defining some weird thing. Maybe it was like n of n to n of n, and you said, I will map everything to 42,84. Okay, this is a function from here to there, but you're really not consulting the two functions that you were supposed to consult to build the obvious function that I want to build. I want to emphasize this idea. I should get the right to say, give me the obvious function from A cross alpha cross beta to gamma cross delta without having to define it always. And this is what we will do as soon as we get to products in... there's a bug in my tablet. Okay, in categories. So, what does it mean for a diagram to commute? I need to emphasize a little point that is usually not emphasized. You write here a diagram, any kind of diagram you like, I don't know. You have some functions, some arrows like that. Okay, what does it mean if I tell you that this thing commutes? No, I will give the answer. So, it was a rhetorical answer. It means the following. It's difficult to get to it, and usually people don't mention a little detail which I want to mention. If you pick some of these things like this to be your source, and some of these like this to be your target, there are various paths that get you from the source to the target. In this is supposed to be the word target. So here is one, you go here, here, and here. Here's another one, you go here and here, and then here's another one, you go here and here. So I have like three paths that get me from this path, from this source to this target. If I say that this whole thing commutes, it means that all paths with the same source and the same target are equal. With a small detail, which is when you're comparing two paths from a source and a target, at least one of the two should be interesting, and interesting means have at least two steps. So if I tell you that this diagram commutes, you should not be able to deduce that this and this are equal. Because if I don't say this small detail, you say, since it commutes, here's a path, source, target, therefore this one is equal to this one. This I want to exclude because it ends up being a very big mess when you argue with these things. You want to understand that, like, okay, if I tell you it commutes, I know that this is equal to that, or I know that if you have like something with a bigger, like A, B, C, D, E, so if you have this and then a bunch of things like that, if I tell you that this commutes, you know that this is equal to that, but you don't necessarily, but let's say you had this. I don't want you to be able to infer from my claiming that this commutes, you should not be able to infer that this is equal to that. You can infer that this is equal to that, yes. You can infer that this is equal to this, it's equal to that, but nothing about this. Because these paths from here to there, both are very trivial. At least one of the paths you are doing there in the commutativity of the diagram should be meaningful, should be at least size 2, length 2. Okay, this is a detail you almost never see. So we know now what it means if I say that the diagram commutes, and I will express a lot of things by saying this commutes. And I will give you some like homework exercises like this one. Express the fact that a function respects this just by drawing a diagram and saying this diagram commutes. The idea is that it expresses, you get equalities out of it, right? Here, which equalities you get? You get that u v I is equal to x, y, z. The compositions, right? Technically, it would be I of v of u is equal to z of y of x. Okay, so you get a bunch of equations and a very good visual representation of the situation. Like, it doesn't matter where you go, all these things go well together. Simple exercise to prove, I will not do it here. It's like, if I tell you, I might tell you in a diagram that a part of it commutes. This is very common. Like, I might tell you this square commutes. That's all you know. So essentially, I give you an equation that this is equal to that. What about this? I don't know. Maybe it commutes, maybe I'm not claiming anything about that. However, a good exercise is that if both of these squares commute, then the whole thing commutes, for example. It's kind of easy to verify. You need to know some laws about composition, and this is like part of what we are getting to. So any questions about this idea of diagrams, commutativity, and all that stuff? Okay, so we have, I think, enough time to just state the idea of what a category is. And I want to give this definition and do some initial constructions, even though I did not do constructions in the posets. We'll try to build these things in parallel. I will only do one construction in posets, which I didn't do, or two. Let's do them quickly. So maybe we don't see the definition now, but let's see. If I have any poset P, I want to associate with it the opposite poset, which I will denote like that, in which I have the same universe. So this is my original thing. And what is the opposite of this? It's again a poset, but it has like the opposite thing, which I will define it. What is the carrier? The carrier is the same. And what is the relation I have here? You guessed it. It's the inverse thing. pretty much the whole thing, if you think of the Hasse diagram, the thing I'm doing is I'm turning it upside down. And it's a construction in the sense that it takes me from posets to posets. This is what I will call construction. Just like you have in groups, you get the Cartesian product, it gets you from groups to groups. These will be the constructions, the big operations, to contrast them with the small operations that you have within each group. Here I don't have an operation. If it was a lattice, I would have, but I'm in a poset, but in any case, this would be a construction. And it makes sense to say, can I have like, if I have a poset P and a poset Q, I can place like one right next to the other, when I have a new poset, where when I'm comparing things inside here, I will consult this order. Where I'm comparing things inside here, I will consult this order. And it takes some thing to write it down, but if you think it in terms of Hasse diagrams, you just place one diagram right next to the other, and this is a new poset. So this would be a new another construction of posets. We'll come back to the construction of posets. I just, I don't know if 5 minutes is good to start this definition. It's not good. It will be bad. Sorry for advertising this. This definition will come on the next class. So let's do a bit, in these 4 minutes, let's do more careful, like some constructions I have on posets. Any ideas? Like I have two posets. What else can I do with them to define a new poset? Arati. What? Well, what would be the answer was take the sum. What would be the sum? Like maybe this is the sum. What? Okay, in the product, okay. We don't have the good like notion of what a product is or what a sum is. This will come in the next class, which we start with the definition of a category. I finally cannot go any further without it. But okay, maybe this thing is a sum. Maybe something here is a product. I suppose that you imagine that the carrier set of the product will be like the Cartesian product of P and Q, but you have to tell me how to compare the elements. Like, what does it mean if I have a P prime? What does it mean that this is less than? How do you compare this with that? So what is your idea here? I don't know, Arati has an idea? Okay, so this is called component-wise product, which you say, I will compare them component by component, and everything has to be comparable, so I will compare these things inside P, and I will compare these things inside Q, and if both are valid, this is a conjunction, then I will say that it's equal. And Arati, did I make a mistake? I think not.
Swap P prime and Q on the left side.
My notation is completely wrong. Terrible. Thank you. So this is a PQ. Thank you. And this is a P prime Q prime. Thank you very much. So this is like. So this is right now, right? Yes. Okay. Now it's correct. Are we okay? So Arati is defining a new order on which carrier the product of P and Q, and we already know this product, okay? So it says, okay, maybe this would be the product of posets, and it's certainly a way to define an order on this set. There may be more than one ways, and maybe there are other ways that they even define things on a different set. Whether one of them deserves to be called a product or not, we discover it in the next class, that we learn what a product is. But so far, I would like at least one more meaningful order here. Yes, Manolis?
Intersection, maybe, because the one above is basically...
Wait, you're talking a different construction?
Yeah.
No, wait. Before we go to...
You mean?
Yes, so I want on the same set, a different way to... I mean, like an alternative to this. Sorry. Yeah. Let's see. Okay. So there is.
P less than Q prime, and.
No, I cannot compare. They are possibly incomparable, right? Because I have a way to compare things in Q. In Q, Manolis, you were saying.
Yeah. The lexicographic
the lexicographic order or the anti-lexicographic order. They are pretty similar. One starts from the right and say, first compare these things, and if you already have an answer, don't even look at P. And if they are equal, then consult P. This is called like anti-lexicographic order. The lexicographic would be like from left to right. And it's one that was used by Cantor, and Cantor picked the anti-lexicographic order for some reason as a defining one. But okay, so we have here lexi and anti-lexi. So we already have three different orders, all of them defined on the Cartesian product of the sets. Which one of them, if any, deserves the name product, we will find out the next time. And I want to mention at least two more constructions, very simple ones. One is that you put P above U, in the sense that you compare everything that is inside P will be considered less than or equal to anything inside Q, and if you compare things inside P, consult P. If you compare things inside Q, consult Q. And maybe this is also a valid candidate for what a sum would be. And another construction now, which is not from posets to posets, but it's like from the natural number to posets. Give me like any natural number you like 3. I will construct this poset. And similarly, I will construct the discrete version of this, which is this poset. So I have, let's call this one plus in a circle, let's call this one plus, and now if I tell you consider this thing, okay, this should be depicted like that. I have 1, above it I have 2, above it I have 1 again, and on the side I have 2 more. Does that make sense that this describes this? I'm hasting a lot because of the time, but so this is the one that plays 1 above the other. So it's 1, oops, sorry. So it's like 1 plus 2 plus 1. I'm done with this. And this is the one that places 1 to the side of the other. So in the end, I describe this poset in this way. And maybe if I had done something like that, this would be like 3. And you realize that now after this, if I do something like up here, you would just need to take this ugly thing and flip it, and now you have this. Yes, final question, and we end the class.
Shouldn't there be a bar above the 3?
Maybe. Yes, thank you. Now, on this tree? Yes, thank you. Sorry. Okay, so that means that at least one person understood what I'm doing. Okay, I will put some like exercise to get acquainted with these little constructions of posets. The next thing we are doing is defining final categories, like Tuesday.